All right, again, I'm gonna show you the antelope, okay, and to the transition to marsupial, okay. Now you see the little thumb back here on the feet here of a deer or an antelope, okay. This is an even-toed ungulate, all right, or an odd-toed ungulate. Well, they're even. These are even-toed. All right. Now look. See how this thumb is and how they're split like that, okay. Now if this lays down. Now look at the kangaroo. This is where the hoof splits, and that vestigial thumb starts to split and grow into 2 extra fingers, or toes, technically. Right here we're talking about toes. See how long they are? Now look how the knee is. It's really close to the inside here. All right. Now you see here's the thigh here, and here's the knee, really close to the stomach, really close. Okay. See how it's really close here? All right. Now this part right here would be where the knee meets the shin. Okay. Here's where the knee meets the shin. Okay. This part laid down. You see what I'm saying? Right here. This whole spot right here becomes the foot. Okay. That lays down. And then it diverges. Okay. Into toes. Now you see how the shoulder blades are here. All right. You see how it's got such a short clavicle right here. Okay, how they're kind of crunched together, the shoulders here. See, they're crunched together because it's standing bipedal, but the shoulders haven't evolved yet. Okay, that's going to happen through when it starts transitioning and passing genes over years and becomes an ape. The clavicle will eventually evolve. Of course, it's still going to primarily walk on all fours, but it can walk upright too. Hence, why apes, orangutans, and gorillas and stuff like that can walk on all fours and upright. All right, now get this, okay? So my theory is, what I'm speculating here or theorizing is that alpha keratin and beta keratin, or mammal and fish ribonucleotides or proteins, are what pretty much create the double helix. All right, the theory is that whales pass an alpha keratin gene, and sharks pass a beta keratin gene. And the adaptive radiation of the sun basically causes these 2 DNA strands to more or less form DNA. It's a protein, ribonucleotides. The cross-contamination between these 2 species, the shark, which is a fish, cartilaginous fish, has no spine, and then the whale, which has a spine, okay? These 2 are more ancient than we could ever know, okay? Obviously, we know how old the shark is. We don't suspect that the whale is as old, but it is. It's at least 200 million years old, okay? Archaeoceti, ancient whales, okay? So mammals and cartilaginous fish, bottom feeders, are the ancient progenitors of the genetic species of everything on Earth. They both pretty much pass genes into each other, and amphibians, reptiles, and mammals walking on the land, or fish walking on the land, are pretty much born, okay? Okay. Beta proteins or beta keratins are characteristics of birds today. There are close connections in terms of genomic regulation between numerous regularly arrayed structures in the epidermis, including denticles in sharks, dermal scales in teleost fish, epidermal scales in reptiles, feathers in birds, and hairs in mammals. Okay, so alpha and beta keratins. Now, all right, now get this. Okay, now this, I'm looking for alpha keratins in whales. All right, for hair. Okay, now look. Now they say that they lost these. Okay, but I believe they gained them as we started walking onto the land. Okay, extensive gene loss and high pseudogenization rate of the alpha keratin genes were identified in cetaceans when compared to terrestrial artydactylians, even in odd-toed ungulates. Okay, average number of alpha keratins 37.29 versus 58.33. Pseudogenization rate 29.89 versus 8%. Okay, especially of hair follicle specific keratin genes, average pseudogenization rate of cetaceans of 43.88% relative to 3.8 Artydactylian average. Pretty much, okay, compared to the toothed whale, compared to the toothed whale, the much more number of intact functional alpha-keratin genes was examined in the baleen whales that had specific keratinized baleen. In contrast, the number of keratin genes in pinnipeds, polar bear, and manatee were comparable to those of their respective terrestrial relatives. Additionally, 4 keratin genes, K39, K9, K42, and K74, were found to be pseudogenes or lost uniquely in cetaceans and manatees. Okay, these genes were what were gained. Okay, these were genes that were passed to grow hair and lose ivory and turn that into bone and hair. Okay, now this is just a theory. All right, but all right, check this out. Okay, now here's the polypeptide structure of the alpha keratin. Okay, now it's basically a half a helix, or it's an overlay. Okay, now here, alpha helix, because it's a protein, amino acid, a basis for life, a building structure. Okay, now beta keratin, a member of the structural protein family found in the epidermis of reptiles and birds. Beta keratins were named so because they are components of epidermal stratum, cornean, rich, and stacked B-pleated sheets. Okay, B-pleated sheets. All right. Now these are analogous to base pairs. Okay, these are like base pairs. Okay, in contrast to alpha helices or alpha keratins. Okay, intermediate filament proteins also found in stratum corneum and rich alpha helices. All right. Okay. See, that's the alpha helix in the beta proteins. Okay. So I think this is where our DNA comes from. These large titan animals, the bottom feeders of the planet, and adaptive radiation and plus forcing evolution through extinction events causes mutations. And these two animals, basically the cross-contamination of genes in the ocean and on the planet, create life, other life, you know, the mutated animals. I mean, macroevolution. You know, you get a whole array of animals. And the longer everything exists and mutates, the more advanced the structure gets. You know, it's primitive at one point, but at some point it just mutates and mutates and mutates and mutates and mutates, and it makes different species. It literally gives rise to different species over a long period of time, and the code gets more and more advanced. And the point, literally, humans are like in this last chain. That's why we're so complex. You know, we're a pretty complex being. I mean, we don't have the most complex DNA. You know, I think it's a mouse or a rodent that actually does, to be quite honest, like the biggest code, other than the axolotl, which is a salamander. And that's an important part of the beginning of our evolution, the salamander. The serpent, the salamander, and the frog. Tetrapods and theropods. I've explained that in other videos. So basically, I think that whales or mammals pass a spine and teeth gene into the reptilian lineage, and the fish or the egg-laying lineage, and the shark passes a polymorphic cartilage gene into us. You know, we're hybrids, more or less. And that's why we're related to everything on the planet, because everything is pretty much a hybrid, or at least we are, because we're the last thing to evolve. You know, we're more or less a hybrid of all of the placental, live-bearing mammals, live children-bearing mammals. And this is the alpha-keratin gene in the mammals that we're passing into this lineage, and they're passing a beta-keratin gene in our lineage. And this whole lineage here lays eggs. This whole lineage here gives live birth. You know, 2 lineages.